In this video, we're going to talk about the famous time dilation effect in the theory of special relativity. Of course, this is not just a theoretical fact, it's an experimentally verified fact. What this one says is that a moving clock runs more slowly. So how is that possible? Let's see. Let's prove that. In order to think about time and length, there's an absolute measure of that. And what is the absolute measure of time and length? That's the measurement by light. So light. Why is the light an absolute measurement of time and length? Because it turns out that light travels at the universal speed given by c, regardless of the inertial reference frame from which it is observed. And so, according to the special theory of relativity, everything is relative except a few things, which includes light. So let's come up with a very simple scheme in which we can use light to measure time. So this is just a simple box here, and let's imagine that at the bottom of this box there is a laser pointer or something like that pointing upwards, and let's say that this laser pointer produces a beam of red light which goes up and then down. And how does it come down? Well, let's imagine that the inside surface of this box is coated with some reflected material. And so we will imagine that this light going up and down repeats again and again, and we can use this event as our unit of time. So let's say that this box has height which is given by h, and let's assume that that's a small number, and when the light goes up and down, we call that one tick. Light goes up and down. Okay, so that round trip event is what we would call one tick. And the question is, how much time does it take? In order to see this time dilation effect, we must introduce some relative velocity. So let's say we're in a reference frame, which is an inertial frame, and we are at rest. We're looking at this clock, and let's say this clock is moving at velocity v to the right, and this velocity is along the horizontal face of this clock, and it's perpendicular to the vertical height of the clock. Okay, so that's the setup. So now let's describe this one tick event from two reference frames. So we're interested in describing this one tick in two reference frames. So first, let's do the simple one first. So first, moving clock reference frame. When we describe this one tick event in the moving clock reference frame, it's very simple. So the clock is, of course, at rest in this moving clock reference frame. So what that means is that, well, it's just as described here. The light goes from the bottom to the top, and then it bounces back to bottom. So that's one tick event. So during that 1 tick event, how much distance does it cover? Well, it's h plus h, so that's 2h. And how much time does it take? Well, we will say that that time is 2t prime. So we will just define it as 2t prime. And what's the speed at which this light moves in that moving clock frame? Well, it's c. It's always c. And so c equals 2h divided by 2t prime. So that means h equals c t prime, or t prime equals h over c. So that's what happens in this moving reference frame. So we figured out what the time, what half-tick time is in this moving clock frame. So that's very simple. I hope you agree. Now let's describe the same event in the rest frame, in our frame, assuming that we're at rest and we are looking at this moving clock. In order to describe this same event from the rest frame, it's actually convenient to consider 3 snapshots here. So let's say that this is at the beginning of the full tick, and then in half tick, let's say the clock moves by that much, and then in another half tick the clock moves by that much. Well, from here to there, from here to there, it's supposed to be the same distance. My drawing skill is not perfect here. So anyway, so we would understand that the light goes from the bottom to top here, and then top to bottom here. So then in our rest frame, how does the light move? Well, clearly it moves like so, and then like so. So you can say what happens to this light is that when it's emitted from the bottom, it actually has the horizontal velocity as well as the vertical velocity. Why? Because it's emitted from a moving thing. It's like throwing a ball, throwing a baseball in a moving train. If you do that, you might think that even if you throw the ball perpendicular to the moving train, it will actually move with the velocity that's parallel to the train as well. There will be that velocity component because it's drawn from a moving frame. It's the same principle here. So now, if you look at this path here covered by the light for this 1 tick event, you can see that, well, that length is, the full length here is definitely greater than 2h. Why? Well, let's figure it out here. We know that this is actually just h, right? So that this length here is definitely greater than h. So this full length is greater than 2h. What that means is the time it takes for the light to go from here to there, as observed from the reference frame of the rest frame, is greater than 2t prime here. Why? Well, because this light travels with the same speed c when we look at it from the rest frame. That's the magic of light, if you like. So this time it takes for this light to go from here to there is actually greater than 2t prime. So we will use t for the half-tick time as observed in this rest frame. So that's the distance that the light travels in half-tick is actually ct. So that's the length of this this arrow here. And now let's finish let's construct a triangle here so that we can actually figure out what is the relationship between t and t prime. And if you consider this triangle generated by these 3 points, this point, that point, and that point, you can see that it's a right triangle, and we figured out these two lengths. And we now ask the question, what is this length here from the red dot to the black dot? Well, the answer is easy, because that's the distance that that this box traveled during time t, and because the box has velocity v, this distance is actually vt. So there we go. We have all the lengths of this right triangle figured out here, so that we can write down the relationship between these 3 lengths using the Pythagorean theorem. So we say c squared times t squared equals v squared t squared minus plus h squared. So we can now move this v squared t squared to the left hand side and factor out t squared, and you get c squared minus v squared equals h squared. At this point we can use this fact h is equal to ct prime, so that's t prime square c square. And so now we can solve for t and t prime, remembering that both t and t prime are positive numbers. And so then you can write t equals t prime divided by square root of 1 minus v squared over c squared. So I omitted some steps here, but you can verify this using a more careful calculation if you like. So anyway, so that's what we found. This factor here, 1 over square root of 1 minus v squared over c squared, that's a very important factor. That's what we call gamma in the special relativity literature. And this gamma is a number greater than or equal to 1. And this v can be 0, or it can be a number that approaches c for any material particle with a finite mass. So this gamma goes from 1 when v equals 0, and it approaches and it increases as v, the absolute value of v increases all the way to infinity when v approaches c. So what this means is that if you look at this equation here, t is generally greater than t prime. So for any finite velocity here, t is greater than t prime. So what that means is that when you watch a clock that's moving, the time that you measure is longer than the time that would be measured in the rest frame of the moving clock. So the time is dilated relative to that of the moving clock time. And so that's the the meaning of time dilation. In other words, the value of t prime is actually smaller than t if this v is finite, and so that means a moving clock runs slow. But this is not just for any clock. This is for any physical process. So in other words, if you're moving very, very fast, the biological clock also runs slow.